All right, record. Okay, so I'm recording now.
All right, sir. Thank you.
We have our simple rectifier circuit that is grounded. Okay, so last class, someone asked about phone chargers. So maybe we can try building something similar to a phone charger now using Multisim. All right, so what are the drawbacks of this circuit? Well, for one, let's look back at our oscilloscope wave. Let's come down a little bit, right? One, we see only half of the wave is coming through, right? Because the other half is cut off due to this diode. So essentially, we're wasting 50% of our energy, right? Which is not very efficient. Additionally, this wave is essentially turning on, then off, then on and off, then on and off, which if we're powering something like a DC motor or something might cause it to behave erratically, right? So we don't, even though this is DC power, right, positive alone, we don't want to send this into an appliance, right? We want to play around with it, fix it a little bit. So first, let's do a full wave rectifier, okay? So there are two ways we can do this. One, we could use a center tap transformer and use two diodes to do halfway rectification on each of the taps, right? On each of the sides of the transformer, or we can use a full bridge rectifier, which you guys may or may not know about, all right? So let me just pull up some schematics here. Okay. This is what a full bridge rectifier looks like. It has 4 diodes. So power will be coming from these two lines, A, B here. When it's, let's say this is the positive side, is the negative. On the positive half, it'll flow out. It'll flow down this diode, across the load, down this diode, D3. So D1 and D3 cause the load, then back in, right? Completing the circuit. Now, when the polarity is switched, right? Maybe we can analyze that as going the other way. It'll come here. It can't go into D3 because D3 is blocking it now. So instead, it'll go in through D2, through the load, right? And then through D4, right? This is a full bridge rectifier. Okay. Now they're full rectifiers, full wave rectifiers, instead of half wave rectifiers. I use center tap transformers. And essentially look like this, where, and of course we'll do them out in Multisim, so you'll see the diagrams clearer. Right? We're for the one cycle, first half of the cycle, it powers the load using this diode, and the second half of the cycle, it powers using this diode, right? Okay. So firstly, let's build a more efficient circuit. And after we build a more efficient circuit, we want to smooth our waveform out, right? So this here is a pretty bumpy wave going up and down, but we can actually smooth this wave out with the same half wave rectifier. All we need to do is drop a capacitor in there. You go place component, basic capacitor, 1 microfarad is good now, and we'll adjust the value as we need. Yeah. Now, if we were designing this on paper, we'd of course need to do calculations for the value of this capacitor. But because we're in simulations, we can just quickly adjust this value, look at our oscilloscope or output waveform, and adjust as necessary and find a good value. Right? So let's just run this. Look at our waveform. Now, it's changing slightly. I don't know if you can see this curve. There's a slight curve there. So the capacitor is helping to pull that wave together, right? Helping to stop the sudden changes, right? Because the capacitor resists those fluctuations in the voltage. Okay, let me just add a switch in here so we can see that better. And let's adjust this value to maybe 5 microfarads. Let's run this circuit. So now this is a waveform with the capacitor not connected. It's fairly half wavy, right? The bottom half's cut out. So when we close this capacitor, what's happening is it's trying to smooth these ripples out. Generally, when designing rectifiers, you would want to do your calculations for V ripple, and the calculations get pretty complex, right? Depending on how advanced the rectifier is. Because we're using Multisim, we can just go ahead and change the values, right? Let's adjust it even higher, right? Maybe something like 10 microfarads. Run again, right? So we see this here is a regular wave, switch is open, and when we close it, it becomes better. It's slowly turning into a smoother wave with less oscillations, with less changes, right? Up and down. Make it even bigger, 100 microfarads. Right. And you see now it's kind of straight. It's not as straight as we would like it to be, right? Usually when we are looking at the DC source, let me place the DC source. It's the same, about the same level, right? Let's make it 100, just so that it's on the same scale. Let's look at that waveform. Oh, sorry, there isn't any load. This says, yeah. So what we see is this here is like the regular DC, and this here is our rippled half rectified wave. Okay, now we can make this circuit even more advanced, right? By, of course, using a full wave rectifier, which we'll do in a few. But we can also add in a voltage regulator. Something like from maybe the LM family. Something from the LM family. So let's place a voltage regulator. But first, maybe let's adjust the value of this voltage to something more usable, something like maybe 9 or 10, 9 volts. So open up this. Here, about RMS is going to be 9 volts. And we know RMS is not the peak voltage. It's just about somewhere around here, right? So to get the peak voltage, we'd usually multiply by the square root of 2, right? So V peak is equal to V peak is equal to V RMS times root 2, right? So this here would be your wave, your sinusoid. And RMS is just a value about here, right? Is a value used to define AC wave, which maybe you guys may have come across. So the peak voltage, the actual peak voltage is slightly higher than that. So just multiply this by √2. So for example, if this was 9 volts, VRMS, which is what we set in our circuit, okay, the actual peak value would be this times 1.141 something, right? Square root of 2, which would be approximately, I guess, 11, just slightly higher, okay, slightly higher. And we can see that from the graph, right? Our scale, 5 volts per division, we see the peak of the wave is actually a bit higher than 10 volts, right? So we just need to keep that in mind when designing a circuit. Okay, now for the voltage regulator. So you can just find out by searching LM 7805. This one should be fine. LM7805 CT. Now, the LM78 family is just a family of regulators from a particular manufacturer, so LM78. So these electronic manufacturers, right, manufactured this, and these here are all voltage regulators, right? And the 05, so usually it's LM78, right? And these two numbers represents the voltage it regulates to. A voltage regulator is essentially just something that if we send in something like over 9 volts or 9 to 11 volts, right? It's going to take that 9 to 11 volts and it's going to output 5 volts. So it regulates the voltage down. So for the case of building a charger, we would want to put a voltage regulator just to make sure that the voltage that we output in is always 5 volts, it's stable. And we want to generate something slightly higher so that in case there's like slight fluctuations in voltages, maybe this drops to like 8 volts, right? We still continuously output that 5 volts. Okay. So let's add that into our circuit. Here, 3 lines, three pins essentially. This is your voltage regulator. There are 3 pins on it, the in pin, the out pin, and the ground pin. This here connects up to ground. This here is the input signal. So this is after a wave is finished rectifying, we send that signal in here, and this here is the output signal, which is where we want to send our load. So in this case, our resistor, right? So let's add the diameter circuit. First, we can delete this line. Put this into a circuit. So here you see we haven't opened up the resistor, but we see that the wave, even though it was about 9 RMS, so somewhere around here, about here, the voltage regulator chops off that half there, right? It just chops off that half there. So that's what the voltage regulator does. It just cuts off that voltage, cuts that voltage down. So if we pair that up with this thing that smooths the wave out, right? This shunting capacitor essentially, put that in there, our waveform should essentially just become a nice straight DC wave. And this is good stable electricity that we can use to power a phone or something like that. Okay, good. Of course, at the end of this, you would want to attach up a USB connection or something like that. You know, all the other electronic stuff, right? And you have to look for the USB pin out, see which pin is 5 volts, which pin is ground. I can show you that, guys, that really quickly. Yeah, okay. So it's something like this, right? So there are four pins on the USB. 2 of them are for data, right? Pins 3 and 2, and the 2 end pins are for power. So USB VCC and USB ground. So this is where you put the positive end, and this is where you put the ground end if you want to attach some kind of USB connector, right? And there are also male and female USB connectors, so you can look up this. So Multisim helps us with the design, and then after we finish prototyping, then we go buy parts and solder up and do everything else we need. So this is the basic half-wave rectifier circuit. What I want you guys to do is to do a full-wave rectifier circuit with a center tap transformer, with a transformer, not a center tap transformer. So what you're gonna do is first you're gonna place the AC power source, and you're gonna place one that's fairly big, right? 120 VRMS. And then you're gonna add in a transformer, just a regular rated transformer. And you're gonna break that down to a more usable voltage, somewhere like 9, anywhere from like 9 to 12 volts should be fine. You're gonna send that in to 4 rectifiers, right? A bridge rectifier essentially. And then after that, after you finish generating a fully rectified wave, then you can add in a voltage regulator and a capacitor for this. So, and you guys can just Google a schematic version of this, but
Excuse me, sir.
yeah.
Yes, sir. Sir, I missed the last class. I didn't get to see when you started the Multisim, right? So
Okay.
I want to know if you post the video on YouTube or anything.
I posted one. I'll post this one and the other one after class maybe. Okay.
Okay, no problem. Because I'm sailing right now.
So, yeah, so essentially we're just building a full wave rectifier. We looked at the half wave rectifier last class. Now we're modifying it, adding in a capacitor and a voltage regulator. And this here is a full wave rectifier. So you guys will build that, and then we'll add in the capacitor and the regulator as well, if you want, right? So that's here. Let's get a multimeter quickly here. Okay, right. So this transformer chops our voltage in half, and that's, of course, we know that's because of the different turn ratios, right? And here, since we have a bridge rectifier, right? So back to that bridge rectifier circuit with 4 diodes in a bridge, this here does full wave rectification. So of course, let's just adjust the values for the channels, right? And we see that this here is a full wave rectified AC wave, right? We don't have that gap in the middle there, right? That we expect from the half wave. So this here is a more efficient circuit, right? Good. So now we need to adjust the turns ratio for this transformer. So just go ahead, make this 60, half of that is 30. Let's try 4. 29, maybe we can do more. Maybe 5. Also, we want to ground the circuit as well. Okay. Okay, good. So I want you guys to take a few minutes now and build this full bridge rectifier circuit. Okay, so you can just go online, look for schematic of a full bridge rectifier, or maybe you know it out your head, or you can just look on the screen and try and copy it, right? But essentially, we're not doing half-wave rectification anymore. We're doing full-wave rectification. So we're using this bridge rectifier circuit, which requires 4 different diodes to be wired up in this particular way, and the load connected this way and the AC lines connected this way. And we're using a transformer to step down the voltage, right? So we're stepping down from 120 VRMS, which is something that you would plug into your mains and collect. So if you plug into a point at home, you might get something like this, or maybe 220, 200, something like that, right? 210. So we're taking that voltage, we're stepping it down to something more usable. We're using a turns ratio of 12. So out of that, we're gonna get a more usable voltage, which is about like 9 volts, which is good, which is a voltage within the range of our voltage regulator, right? Because this voltage regulator is specified for input voltages around like 9 volts to 12 volts, right? Good. So what I want you guys to do now is just build this circuit and then add in the capacitance and the voltage regulator so that you can output a nice clean 5-volt wave. All right, so take a few minutes to do that. If you have any questions, you can't find any parts, can't find the transform, stuff like that, go ahead and ask me. Okay, and I'll help you out. Okay. Any questions? No?
No, sir.
Okay, good. Take a few minutes to do that and we'll move on to filters or something.
Sir, the key space, sir, and the U1. We typing to find it.
Key space.
Yes, sir.
So this is a switch.
Oh,
And so when we're simulating, like I press play, and then on my keyboard, I press the space button. It toggles. I don't know if you can hear the key being pressed, but it toggles the switch open and close. Right? So it's S1, switch 1. The U is the voltage regulator. So place component. Basic. In here, you'll see basic, virtual, whatever. At the bottom resistor, you'll see switch right here. Right, this is a regular single pole switch. There's single pole double throw switch, which switches from single pole double throw switch. Essentially, it's just a single pole double throw switch, right? And the one you want to use is this single pole single throw switch, which is just a regular switch essentially. And there are all kinds of other stuff. They're like dip switches, which you may or may not want to use as well, right?
hold on, sir.
Okay.
Hold on.
So in switch here, at the bottom,
I found a switch, sir.
SPST. Okay, good. Now for the LM, I can't remember where it is. It's LM7805.
It's all
I don't-
families.
So it's somewhere in power. Yeah, power, voltage regulators. Then you could scroll through here if you want, LM7805, or you can just type it at the top here.
Okay, hold on, hold on. Power, voltage regulator. LM7805 CT. Yes, sir, I got it.
Sir, are all the diodes supposed to be facing upwards in that direction? Or it doesn't
Yeah.
matter?
Yeah, no, it does matter. They're supposed to be facing upward that way. Let me open a backdash schematic of a bridge rectifier. So essentially, this is how they are, right? So these two are both pointing this way, right? So even though they kind of in this nice, neat, cute little triangle, right? These two are still pointing up, right? So in the same general direction. So are these two, right? In the same general direction, right? So both of them pointing this way, both of these pointing this way. So they're all pointing to the right-hand side of the screen, even though they are slightly at the angle, right? And you connect AC of those two sides and DC of these two sides. So they're pointing that way. So our version is rotated upwards. So all of them pointing upwards. The DC out from these two ends, the AC out from these two ends. So it's just a matter of converting this visually pleasing schematic to something more workable. I think you can rotate these an angle. I'm not too sure. Let me see. Yeah. Maybe if you go in and try and edit the properties. Yeah, no, there's no way to rotate it 45 degrees. Right? But it's just a matter of converting the schematic, right?
Yes.
And we can see our circuit works by opening up our oscilloscope and seeing, okay, we don't have that space there anymore. Remember the half-wave rectified version, we had that space. We had a wave, we had a space, we had a wave, we had a space. You can probably drop that in on the B channel. You guys. This is the rectified version. Okay. So that's not gonna work. That's the rectified version. I can open this. I can delete these two lines. And I can connect. So on channel A is the full wave rectified signal. So if we turn that off, we're left with channel B, which is the half wave rectified signal, right? So you see there's a space in between the waves, between the different humps, where the bottom half of the wave is cut off. So if we turn that off and turn this one on, we see that the bottom half isn't cut off, but it's flipped upwards, right? So it takes the energy from that bottom half and reverses the polarity of it, right? So we don't waste it. We don't just cut it off and throw it away.
Sorry. Where's do again if we get your circuit to run?
Get the circuit to run.
Yeah.
You press this play button right here.
And if it's a highlight,
If the play button is not highlighted,
yeah, if it's not highlighted,
is the red button highlighted?
the stop
Is,
button?
is this button highlighted?
No, none of the above is highlighted.
None of them?
Uh-uh.
Really? That's weird.
Yes.
Try coming to simulate and run.
Same thing. It all blank off.
Are you the person that just tried and cracked the trial?
Yeah, I am. I activated the thing.
So close it and open back and see. Save your file,
No,
close it and open.
what happened, right? I saved the file and the other. I have two design projects, right, on the same file, right?
Mhm, mhm.
And one called rectifier, one called bridge rectifier, and the rectifier one they're highlighted, but the bridge rectifier file I just created is not highlighted.
Huh. Weird.
But it's saved. That's the whole thing. It's saved. I don't know.
Oh, is the other one still running? Yeah. Ryan Waldron.
I just checked it, but it's not running. It's on
Huh.
pause.
Pause.
Okay, I just stopped.
Well,
Yeah, I
stop
just
it.
stopped.
Stop it. Stop it.
All right.
Don't pause it. Just stop it and see if the other one turns on.
Yeah, the other one turns on. Yeah,
Okay, good. Problem solved. Great.
great. Thanks. Thanks, Ryan.
It's Ryan. Ryan figured it out for you. Good.
Yeah, Ryan. Big up.
I'll give Ryan an extra mark. Okay. Okay, so when you guys finish with that, drop in your capacitor and your voltage regulator, right, into this bridge rectifier circuit. And then if we have some time, we'll look at a low pass filter and do some AC sweep stuff.
Excuse, sir.
Yep.
Sir, you could just go back through the demonstration how you install in the voltage limiter.
The voltage regulator. Yes.
Yeah.
Okay. So, okay, so I said before this voltage regulator is called the LM7805 from the LM78 family. 05 here represents voltage, so this regulates the 5 volts, right? Okay, good. So now this is the LM7805 voltage regulator, and it has 3 pins / connectors that we want to call them, right? So now in this side is the input signal. This side is the out, right? The output signal. And this here is the ground. Now remember, as we said last class, I think it was Tuesday, ground is just a reference. So internally, whatever the input signal is, they both share this common ground, right? So let's rename that as common ground. Common ground, right? So here is where we're going to put the input signal, right? So remember, a load is the resistor. And right now it's connected up. So our rectifier is here, right? And it's connected up to that. Here has our AC source. Let's just put it like that, right? So this here is connected to our resistor. So in order to install this voltage regulator, you need to take that load out, right? You need to connect, this here was the input signal, and you want to send a regulated voltage out. So you need to install a regulator here. This here is going to be the inside for the input. This here is going to be outside for the output. And then you connect up this ground to the common ground of your circuit. So this is the line where you have the ground in, right? Common ground of the circuit. Okay, so this,
Sir, could you go back to the diagram? Let me see if
this is how it is essentially, right? Good. So here, to have a regulated wave, we need to come here, connect up there, connect up here. Oh, we need to put a capacitor in place. So now you see, this here is a full wave rectifier, the circuit, which is down below connected on channel A. Let's go ahead and turn that off. And this here is the DC, smoothed and regulated half wave, right? That's a nice smooth line, nice smooth DC line we have there. Okay, good. So that's essentially connecting that up. So what you're gonna do is you're gonna do the same thing that we did up here, down here. And I think you guys can figure out how to do that, right? You would wanna break this line and then do some stuff, right? Yes, you guys can figure it out, or you want me
figure out what, sir?
figure out how to put the regulator into this circuit?
Hold on.
The same way we put into this circuit. Let me remove the. Let me remove it. So this is it here, right? And this is it here. This here is your load, right? Let's rename this. Let's rename that as load, right? Okay, good. So this here is your smoothing capacitor, your voltage regulator. So you want this stuff. You can do it piece by piece. So you can first do a smoothing part. You want this stuff in this circuit. How do we do that, right? Engineer, like you've been taking electrical engineering classes. How do we move from this circuit to this circuit? How do we get this regulator into here? Where do we put it? where do you put this capacitor into the circuit, right? You guys can figure it out. It's not too hard, right? Yes, no, you know where to put it.
We're gonna see, sir.
All right, put it and try it out. Like, don't doubt yourself, man. You guys know where to put it. Well, I'm sure how you're thinking about putting it, that's the way it's supposed to go.
So
Right?
how
If
did
you-
you how do you find like the never mind, it's potentiometer.
Oh, the multimeter.
No, the transformer and the thing next to it. I think I'll find the transformer. What was the name of the transformer, sir?
Transformer.
Yeah. Is it 1P, 1S?
Rating. See rating.
Left.
We'll just-
Rated transformer. Let me just type the name. It's in.
Gotta get two, ano, yeah. They get a CT and I get a rated one.
So just like your regular transformer, yeah. So there's the CT, which is the center top, right? Which is where you used to do your the rectification with 2 diodes, right? And then there's just the regular rated transformer.
So red.
Now the center top. Center top has three lines and rated has 2 lines. Okay.
Alright, so wait. All family transformer.
Rated.
And the AC. Oh, never mind. I think I remember though. Hold on, sorry. The
Yes.
multisim stop responding.
Okay. Don't pressure it. So it's in sources, power sources, AC power, right? AC power.
Hmm.
Sir, what were the changes you made to the transformer?
Was someone saying something?
Yes, sir. What were the changes you made to the transformer?
Oh, yeah. So the turns ratio is 12. So value on the value tab, right? Turn primary to secondary turns ratio is 12. You guys maybe cover this in electrical fundamentals. The turns ratio of a transformer, right, is just like how do we set the voltage on the other side of the transformer, right? How many turns we use. Yes. Okay. Yeah, so just set the turns ratio still. Turns ratio just specifies if this voltage here is 120, how much is this voltage out on this side gonna be? Okay.
Okay, sir. Thank you.
Different turns ratio would give you different output voltage. And it's just how many times you wrap the coils around on one side versus on the other side.
So what scale we using for the graph? For the oscilloscope?
Sorry, your mic was muted just now if you were saying anything.
Oh, sorry about that. Yeah. So what I was saying is that your this signal here, we set it up and we know it's gonna come out about 9 or 11 volts. So just make sure you can see that. And you can just do that by just playing around with the scales, whether it's going up or down, right? And depending on what you're seeing. Just put the scale as used. It could be 10 volts per division or 5 volts per division, whichever one you feel like doing. Right? And make sure it here is set to DC, right? And not 0 or AC, because nothing's gonna show up. And AC is gonna have it like this instead of on that center line. Additionally, you might see something like this, right? If you see something like this or like this, just turn the time base down to a reasonable level. Or you might see something like this. If you see something like this flashing across the screen, then you know you need to adjust the time up a little bit. Okay. So play around whichever scale is good for you. Okay. This is also a perfectly fine scale, which is this too, maybe after you finish stopping it. Yeah. This is a perfectly fine graph to look at. Okay.
Yeah. So this simulating assignment, right? It's really forced, right?
Gonna be what?
The Simulink assignment, the due forest, right?
Simulink assignment. Oh, Simulink. Yeah,
about,
it's due the 2nd.
The second?
Yeah,
All right, good.
the Friday we have class, which should be our last class as well.
All right, good. Respect.
Yeah, I saw some students submitted theirs already. That's fine as well.
But them is the students who know to do the thing.
Okay. I mean, there's 6 people in the group, so one of you guys should know Simulink or should be able to learn it fast enough.
Hey, YouTube is it?
Yeah. I mean, it's software. You guys already have some engineering knowledge in there, so it's just about applying those concepts towards the software. Right? Software is there to help you in your design process. So if you have some idea that you want to use Simulink to help you help you reach some kind of goal, something you want to design, then use Simulink to help you design it. Right? Like with Multisim, you want to build a phone charger, right, Dawson? Or you can use Multisim to help you design a phone charger, which is kind of what we're doing today.
Yes, sir.
Yeah. So usually they don't use individual diodes to do this stuff. They would use something like a bridge rectifier package. It's like, it's this thing that comes with four pins, and essentially this here has all four of the diodes inside of it, right? So instead of you having to wire up individual diodes, this has all four of the diodes in it, something like this, right? Has all four diodes in it, and they just pull out the four leads, right? So inside of that little square thing, right, would have your rectifier with all four little diodes, right? And then outside would have the leads that you connect up to, right? And they of course would provide some data sheet telling you which pin is which and how it's connected up, whether this is pin 1, pin 2, pin 3, pin 4, and it's generally like a dot or a little cutout or something to show to line up the pins for you. Right. Like in this one here, it's loading. There's this little dot to show you, okay, this is that pin, this is that pin, this is that pin, right? But for just general purposes, we'll go ahead and use individual diodes. So is anyone finished with this full rectifier circuit?
Yes, sir.
Good. Did you add in the capacitor and the voltage regulator?
Mm-hmm.
And it works? You get a
Yep.
nice wave? Okay.
Wait, hold on.
Hmm.
Sir, can I show what I have?
Okay. Go ahead, share screen. Let me stop. Are you allowed to share?
No, you still disable it, sir.
I turn it on.
Okay, let me see. Is that way it's supposed to? Is it supposed to be so low?
Adjust your scale, man. Remember, we use the transformer to drop it down. Your transformer ratio is 2. So this should be about 60 volts coming out this side. So drop this scale down in your channel, whichever channel your thing is connected up to.
Okay, I believe the transformer is channel B. So I'm gonna drop the scale.
Go down.
Never mind.
Okay, so you put a capacitor in, right?
I'm
And
the shift. I'm there.
The capacitor is channel B. The channel A is the transformer.
Get
We
this
got it
view.
because let me see. Look, drop it.
okay, close the oscilloscope. Let me look at your circuits real quick. Okay, so channel B is the top circuit, channel A is the bottom circuit. Okay, open up back your oscilloscope.
Yeah.
So under channel A, you'll see AC 0 and DC.
Mm-hmm.
You'll see AC 0 and DC.
Mm-hmm.
Press DC. Okay, good. Now turn off the top circuit. So on channel B, just press 0. I'll turn off the top circuit. Right, so you see that line. Now adjust your scale on channel A now so that we can see this waveform. Okay, good. So now this is our full rectified signal, right? See no spaces, right? No spaces in between that. So now to this,
So
add
this,
your voltage regulator, add your capacitor. Okay.
the capacitor is closed. Wait, so we want me to do
No, you
connect the
remember the-
voltage regulator now and close the capacitor?
No, so you know that this top circuit is different from this bottom circuit, right?
Yes, sir.
Good. So what we're looking at right now is the bottom circuit.
Oh, so this is the
Full
transformer.
rectified. Yeah, the full rectified way. Those diodes rectify it a certain way. All right. Good. So, okay, open the capacitor.
So open the capacitor. Good.
Good. And turn on back the second one.
Channel B.
Press DC. Press DC. Turn on back channel DC. Good. Now turn off channel A. So you see this one, how it's in half wave rectified signal. There's a space in
Mhm.
between the bumps. So good. Now turn the other one back on. Turn channel A on. Okay, just press DC. Good. And turn channel B off. You'll see. Okay, you see how this one is, there's no space in between.
Mm-hmm.
Good. Now from this, take the capacitor.
Is better.
Yeah, good. So take the capacitor and put it in the bottom circuit as well as the voltage regulator. Put in the bottom circuit so that we can get a nice smooth DC wave, right? A nice smooth DC wave.
So you want me to take this capacitor?
Also what you need to do is change the turns on this transformer. So close the oscilloscope. You need to stop simulation before you change stuff, right? Change that to 12. Primary to secondary turns ratio to 12. So go down, 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 down to 2, where you see 2. Yeah, there, change that to 12. Okay. Press OK. Okay. Now you can just
That's okay.
Yeah.
I did.
Now just plop your multimeter, verify that the voltage coming out is in between the range of 9 to 12. Because we can't just go ahead and throw our voltage regulator in with a really high voltage like what you had just now, right? Because you had a voltage that was about 60 volts or something like that, right? Which is a pretty high voltage.
Where you want me to look for? Where you want me to put it?
At the output of the transformer. Yeah. Good. Now run it.
Fluctuating millivolts. Well, in DC it's 3 point something.
No, so RMS is 6.6 volts. That's good. Okay, we'll see how it regulates, if it regulates well. No, it's 8.8 volts, right? I can't see.
Supposed to be 8.8.
Is that it? 8.8?
No, sir. VRMS is 6.66. VDC is 3.87. Frequency is 60 hertz. V voltage peak to peak is 14.1. And the top one keep fluctuating in millivolts.
Okay. Okay.
All right, so let me see how it looks on the oscilloscope now. Wow. Hold on, wait, let me so So channel A is the rectifier. So this is the rectifier without space. Turn this off. Channel B now is the one with space.
So we're only worrying about the bottom one now. We kind of just want at a level that we can send a rectified signal into it. That's essentially all that we want. So we just need to make sure our turns ratio is at a reasonable level and adjust if necessary. So turn off channel B. Let me see.
Channel B is off.
Okay, that
So the
seems good.
bottom one.
That seems good. So that there, now just add your
Mhm.
capacitor in and add your regulator in and let's see what's okay.
All right, that's a bad idea.
You can delete the lines, and you can copy components.
Yes, everything's slow, sir. It's slow. I'd
You
already
can go
delete the
ahead
line or
and
anything gone off.
you can go ahead and stop sharing. It should work because other students said they did it already and they got it.
So am I supposed to get a straight line when I put a capacitor and the regulator inside?
Yeah. You can do one first, then the other, or both. Okay. So you want to
cool.
stop simulating before you move stuff around, right? So you want to go and press that stop button. Yeah. Now you move stuff around. You don't just move stuff around while simulating. Imagine if you're powering your circuit, right? And then you just go and pull out your capacitor and plug it in on another part of the circuit board. Something's gonna go wrong, right? You don't just want to go moving parts
So,
while simulating.
So this is how I would put it in. Like you said, how we're supposed to put it in. This is how I would put it in. Am I putting it in correctly?
Let's see. That part's the ground.
I have a,
Good.
I have a feeling that something is wrong, but no.
No, let's just do the regulator alone first.
Regulator alone. So okay, good.
Yeah, let's do that alone first. One thing at a time.
Do I need to connect these two lines in? These two,
Yeah.
the line voltage in?
Yeah.
All right, good.
Not there. Come on, at the top. Not there. No. Okay, good. I need to delete that short. There's a short in between the in and the out.
Sir, just get knocked out. Hold on, the laptop coming in back. This is my
Okay.
cell phone.
Okay. All right. I'll put the regulator in my circuit. Okay. So when doing this, making changes, you first want to just stop your simulation before you go moving stuff around, right? You don't want to change it while the simulation is still running. And you want to keep stuff neat so you can just move around the components, making space for the ones you're going to add. Okay, good. Now, we know that our voltage regulator is supposed to come taking the input. So maybe I can draw a line. everything before this line is our rectifier, right? Everything after this line is our load. This stuff's a this stuff's a rectifier. So what we want to do is we want to take our input signal, our signal from the rectifier, send it into the regulator, and send that output signal into our load. So when bringing a rectifier down, let's place it here. We want to take the input signal from the rectifier and send it into the load. And then we want to connect up this common ground to ground in our circuit. So this here is our signal coming out of the rectifier and then sending that in to our load. Okay, good. Then we of course want to connect up to the common ground. Connect everything up to ground. Connect up this common part to ground. Okay, good. So that's how you put the regulator in. Now let's just look at how that changed our waveform. Connecting up our oscilloscope, running. So now we see the same thing that we saw in the half wave rectified circuit, that anything above 5 volts gets chopped off, right? So we chop off anything above 5 volts. Now we also want to try removing these ripples, right? This up and down, this fluctuation. We want to move from something that's like this, up and down, to more something like that's like this. And we do that with the capacitor, right? We use the capacitor to help smooth that wave out. Okay, good. So first, I would say let's just remove the voltage regulator for now. Connect back our old signal. And look at it one more time what it used to be, right? Let's play. This is our old signal, and this is what we want to smooth out, what we want to get rid of the ripples from. So in order to do that, we need to apply the shunting capacitor here. So again, this here, everything before is rectifier. Just like here, everything before here is rectifier. This here is shunting capacitor. This here is regulation phase. And this here is load, right? So let's do the capacitor load. Like this capacitor, paste in. We want to add the switch in as well because we want to toggle it. You don't have to add the switch in. You can just go ahead and put it short.
Sir, we supposed to get with the regulator inside a square wave or something?
A wave with it chopped off every 5 volts. At 5 volts.
Okay.
Change this value down to something more reasonable, like 50.
All right, sir. Hold on. Wait, please.
So we now have this wave it still has ripples, but it has enough stability so that when the voltage regulator comes in, it can just smooth everything off, just chop off everything above 5 volts and not have any kind of variation for stuff below 5 volts, right? So you can just come in and chop everything off, right? Maybe we can up it a little bit, something like 20 or 30 microfarads. When designing this on paper, you'd have to do a calculation, but we can just average maybe 25 microfarads would be a good value. Simulate again, verify. That seems like a good value, and then we can just come with a regulator and chop everything off. Okay. Now, the same way we add the regulator in last time, the same way we're gonna add it in now. Right, so everything before here is rectifier circuit, right? AC source, transformer, rectifier circuit, everything before there. Then we add in this shunting capacitor, which is supposed to smooth the wave off. Now everything before here is rectifier, shunting capacitor. Everything after here is load. So in order to connect that, we need to break this line, connect up this voltage regulator, right? Line it up because we want everything kind of neat. Connect the out to the load, connect the in to the input signal, connect up to this common ground, right? That there's our voltage regulator. Now when we run and have our oscilloscope connected to the output, when we run that, we see a nice smooth DC wave. Nice smooth DC wave. You can reverse that. It's nice smooth DC wave at 5 volts, right? Which is 5 volts per division. That's where the division line is, 5 volts. And we can also just stick a multimeter at the end here. Click on our multimeter, right? And we see the voltage is about 5.02 volts DC. AC doesn't really recognize it as an AC value. But DC is just 5 volts. Okay. So that's how you add in the regulator and the capacitor. So is everyone clear on how to do this?
Yes, sir. I just have one question. Why is it that when we insert the capacitor, we had to insert it in parallel with the resistor?
So it's a shunting capacitor. What a capacitor does is it resists changes in the voltage. So so you guys know how a capacitor works, more or less. Right? Let's say we have some circuit, some battery connected up to some capacitor. A capacitor is essentially just 2 plates, right? 2 conductors with some kind of dielectric or insulator in between them, right? So here does not conduct, does not conduct. And let's just complete the circuit, right? So this is a plate. This here is a plate. Here is just dielectric. Pretend it's ear or something like that. This here is a metal plate, a conductor, metal plate, a conductor, and inside is ear that doesn't conduct, right? If you plug it up to DC, right, it's essentially gonna act as an open circuit, right? Even though it has power, electricity is not gonna flow here. It's not gonna flow here because it's essentially an open circuit, right? But now with AC, what happens? So with DC, there isn't any current flow after a while. There is some small transient flow. So in this DC case, as soon as we plug up the circuit or turn on the circuit, there's going to be some minor flow of electrons coming to this plate, positive electrons, let's say. Positive charges or holes or whatever, and then some negative charges are going to build up here. But that's the extent of it because they can't go over, right? They can't go over, they can't jump across this insulator without having really high energy. They can't jump across. So they're just gonna stay there. They're gonna stand up at the fence, right, and say hi to each other, but they won't be able to cross over. So essentially, after this small initial change, right, time is very, very small, right? It's very, very small. The initial transiency after that initial movement, just aligning electrons and charging up this plate. After that, there's no other movement in DC. Now for AC source, right? We can think of it that isn't exactly how AC works, but we can think of it as this side being positive, this side being negative, and then it's switching to this side being negative and this side being positive. So what's gonna happen is gonna build up charge, and then when it switches, remember it's gonna build up positive charge here, and negative charge here, and then when it switches to here being positive, these are slowly one by one gonna start coming back to this side, because remember opposite charges attract, right? If this was negative, like how it was before, it would go and it would seek out this positive potential difference, right? So it would go and it would pace up onto that plate waiting, right? But because this is constantly changing, when this changes from negative to positive and this has a negative build up here, slowly, electron after electron are going to leave this end and go back to this end. So that there is the discharge cycle of the capacitor. So a capacitor, usually the circuit's off. When we turn it on, it's going to charge up, then it's going to discharge. Charge up, discharge. Charge up, discharge, right? So what happens is that when we charge up, essentially, and when it switches back, it discharges slowly, maintaining a voltage across here, maintaining the positive kind of voltage across there. It resists this, it resists changes in the circuit, right? You can think of it as like a pipe, right? Flowing water straight through, right? Water is going to flow across, right, through this pipe. Now, if you were to move this pipe and say, okay, water is flowing into a tank, right? And this tank here is going to fill up. And it's flowing out, water is flowing out. Water is flowing out, right? So water comes in here, flows out the pipe. If we turn this off for a little bit, for some small amount of time, right? Very small amount of time, this capacitor has energy stored in it that will slowly dissipate, right? So this water in this tank needs to run out before this pipe stops flowing. So when this is constantly turning on and off, so it's switching from positive to negative, we still have some charge flowing, right? So what the capacitor does is instead of going up and down, up and down, up and down, it resists that and kind of says, hold on, I got a little charge, don't go all the way back down yet, right? Then when on the up cycle again, it's gonna build up again. And then when it starts to go down, hey, no, don't go down. I still have a little bit of charge. And the up cycle is gonna charge up again. Then when it tries to go down, it says, don't go down, I still have a little bit of charge. Let me slowly flow. So it's like this tank that charges up, right? So when it goes down, the capacitor is there, it still has charge inside of it, slowly dissipating, right? Slowly dissipating. Does that make sense? Kinda? Yes, no? The capacitor stores charge and we use that to level stuff off. Okay, so we put this capacitor here, it's called a shunting capacitor. That's all it is. It helps resist the change, the fluctuations in the voltages. Because again, with this analogy, water flowing into a tank, right? Even though we turn this pipe on and off, when the pipe's on, the tank gets to fill up, right? So that water flow isn't disrupted on this end, right? Isn't disrupted. Water isn't going what is on and what is off, and what is on and what is off, or what is on and off and on and off and on and off. It instead balances out. Instead averages out. Right? Has some storage built into it. That's essentially what it does. Capacitors are just plates to store charges, right? Yeah, any more questions? Did everyone get this to work?
Yes, sir.
Yes, done it, sir. Hold on.
Okay.
Was experiencing a problem with it because I had the capacitor in series. That's why I asked why it had to go in the parallel.
Oh, so if it's in series, it's not gonna work the same way.
Yeah, it was still giving minor fluctuations.
Yeah. So it's we'll
So it's
cover
actually
next, coming back to the same thing.
No, like yeah, like what you explained when you said you get like a minor, like a slight charge when you connect to the DC, whereby like you know when it build up at the plate,
Yeah.
right? It was getting like a fluctuation of like couple millivolts. It wasn't going up higher than like I think it was like I can't remember the exact value. It was like very low.
Yeah. Mm-hmm. Yeah, so it operates differently, like in series from in parallel. The same way, like, okay, let's say, let me get new. So let's say there's some battery source here, right here, and there's some resistor here. And then if this here is 12 volts, and then here to here is also 12 volts, right? But like here, if you put a resistor here, right? Here to here, if this is 12 volts, is not 12 volts, right? This is not 12 volts. So it operates differently. It's just that a capacitor is a bit more complex an element. So there's a lot more going on. Next class, we'll do filters. So we'll see a capacitor in essentially parallel, and then we'll see one in series as well. And then we'll see how that affects switching it from a low pass to a high pass. Okay, but essentially it has to do with impedance, so regular series impedance, Z plus Z versus parallel impedance, which is 1 upon Z times 1 upon Z plus 1 upon Z, right? But in resistance cases, which is what you guys were exposed to, I don't know how much you guys know about impedance. This would be R plus R for series. And this would be R total. This is 1 upon R plus 1 upon R. Okay. And again, for capacitors, it's actually like 1 upon XC, where XC is 1 upon omega C, and omega here is 1 upon 2 pi FC. So it gets a bit more complicated to see clearly what's going on when we have a capacitor in series versus parallel. I know that's not answering your question, but maybe we'll get some clarity next class when we do filters, right? And we do the AC sweep, maybe. Okay, so I'll stop there today. We'll do the filters next week Tuesday. In the meantime, you guys can practice or finish off your assignment. All right, but that's all I have for you guys. Enjoy the rest of your day. It's Friday, maybe go out, have some fun. Come back next week, you got maths tests and all that stuff. Right? Good. So that's all I have for you guys. If you don't have any questions, you can leave.
Sir, but what the wave supposed to look like? But not the wave. Never
The
mind, sir.
output?
I believe Yeah, I believe I have everything in line with what you're supposed to say in there. So yeah, I just gotta bring the multimeter out now.
I mean, multimeter is just whatever is used to check the volt. Oscilloscope does the same thing.
Are you getting a straight line? A straight line.
As we're supposed to get.
All right, cool. No, but mine is flat in the center. It's not above the whole thing. I adjusting the thing to it, not moving up. It
What
just
do you
keeps
mean
staying
stuck
flat.
in the center?
As in, you see the black line? The
Mhm.
black line is right there. Yeah, that's where it is. It's not going higher than that, no matter how many times I adjust it.
Is it on like this?
Yeah, like that.
Switch this to DC and make sure your oscilloscope is connected to something.
Both of them in DC, sir. Yeah, I take out the other one for channel B too. I take
Okay,
out the first
share
circuit.
your screen. Share your screen quickly. Let me see. Okay. The rest of you, if you finished and your circuit works, you can leave.
Hold on, wait, something I do wrong again. Something is wrong.
Stop sharing.
Sir, will you upload this video before next Tuesday?
Yeah, I'll do it. I'll upload it.
Because I
soon
missed a
after.
great deal. I missed a
I got
great
it now.
deal.
Okay, works. All right.
I got
Yeah,
it.
I'll upload this
I got
right
it now.
after. Okay, good.
Thank you, sir.
What was the issue? I wasn't looking at your screen.
the issue. The scaling with the thing, sorry. The scaling was the issue, but I figured out the right one.
Why are you at 20 megavolts?
Don't worry about this, tell me. I type in the thing, keep going up, and the thing went all the way up. Supposed
Right,
to be
no
low.
worries. We only got
Sir,
like 2 more classes. All right.
channel A is it, sir? Yes, sir. But I want to learn and know the thing too, sir. I don't want like just do the class for the sake of doing the class. But sometimes
You'll-
things try to learn you, like you just don't catch it.
Okay. All right. Yeah.
So we'll be having any other assessment. As you say, we have 2 more classes, so we'll have any assignment or anything. A multi.
Yeah, maybe I'll give you guys to build a small electronic circuit. Yeah. Or you guys want to do like a design a little electronic system in groups again, or just individual? What do you want to do?
I would.
I'll choose.
say-
I'll choose if you guys don't want to figure it out. We'll
Sir, I
talk
would
about
say
it next
group.
class. Okay.
With,
Well,
next time.
because it'll just be like build something you want to build. Essentially, you know my projects and assignments are. Yeah, just maybe you have some idea that you want to realize simulation wise or electronics wise, something, maybe some RF transmitter or something like that that you want to build, or something from one of your classes that you want to simulate. You can go ahead and do that for the assignment. All right, I'll send out an outline with everything to you guys a bit later. All right, good. So enjoy the rest.
All right, sir.